Welcome to this explainer on the reactions of acids. If you're gearing up for your GCSE Chemistry exam, you are in exactly the right place. We're going to break down everything you need to know from this key part of the syllabus.
So what do you think? A fizzing metal, dough rising, salt crystals, what's the link? Well, the answer is a really specific set of predictable chemical reactions. And believe me, by the end of this, you're not just going to understand them, you'll be able to master them. Okay, let's dive in.
All right, so here's our plan. We're going to follow the AQA specification pretty closely. First up, we'll look at how acids react with metals. Then, it's all about making salts through neutralization, and we'll walk through that all-important required practical. After that, we'll get our heads around the pH scale, and we'll finish up with the crucial topic just for you higher-tier students, the difference between strong and weak acids.
Right, let's kick things off with the most straightforward reaction you'll see. What actually happens when you pop a piece of metal into an acid. This right here is the golden rule you've just got to remember. Acid plus a metal gives you a salt and hydrogen. You know, if you've ever dropped a piece of magnesium into acid in the lab, all that fizzing and bubbling you see, well, that's hydrogen gas being made right before your eyes.
Now, for you guys on the higher tier, you need to dig a little deeper. You have to know that this is a redox reaction. Redox sounds complicated, but it's really just a mashup of reduction and oxidation happening at the same time. In our reaction, the metal atom loses electrons. That's the oxidation part. And where do they go? The hydrogen ions from the acid gain those electrons, and that's reduction. The easiest way to remember this is the old classic, oil rig. Oxidation is loss, reduction is gain of electrons. Simple as that.
Okay, so let's move on to one of the most important types of acid reactions out there, neutralization. This is the go-to method for how we make most salts in the lab.
So what is neutralization really? Well, it's pretty much what it sounds like. It's when an acid reacts with a substance we call a base or an alkali. The base basically cancels out the acid, which brings the pH closer to 7, that's neutral. And in the process, you get your two main products, a salt and good old water.
This table is super useful because it sums up the three main types of neutralization reactions you've got to know. And hey, are you spotting a pattern here? Look at the first two. Whether you react an acid with a metal oxide or an alkali, you always get salt and water. But check out what happens when you use a metal carbonate. You get an extra product, carbon dioxide gas. That's what causes all the fizzing in that reaction.
And you know what? The name of the salt you're going to make is actually super easy to predict. It all depends on the acid you start with. So, hydrochloric acid always makes chloride salts. Sulfuric acid always makes sulfate salts. And nitric acid, you guessed it, it makes nitrate salts. So if you react, say, copper oxide with sulfuric acid, you're going to make copper sulfate. See? It's a predictable pattern. So, let's zoom in a bit. What's actually going on with the individual particles during neutralization? It's actually beautifully simple. The hydrogen ions from the acid, the H+, meet the hydroxide ions from the alkali, the OH-, and they react to form H2O, water. This little ionic equation right here, well, that's the heart of every single acid-alkali neutralization.
Right, time to see how all this theory actually works in the real world. Well, the lab world anyway. This brings us neatly to one of your required practicals, how to make a pure, dry sample of a salt.
This 5-step method is something you absolutely have to know inside out. First, you gently warm the acid just to speed up the reaction a little. Then, you add your solid base, maybe copper oxide, bit by bit until no more will dissolve. We call this adding it in excess, and that's so important because it makes sure every last bit of the acid has been neutralized. Next step, you filter out all that leftover unreacted base. What you're left with is a pure solution of your salt. And finally, you gently evaporate some of the water, and then leave it to cool, which lets those beautiful, pure crystals of the salt form. So we've been talking a lot about acids, but how do we actually measure how acidic or alkaline a solution is? Well, that's where the brilliant pH scale comes in. And it all comes down to two little ions. Acids, when you put them in water, produce hydrogen ions, or H+. The more H+ ions you have, the more acidic the solution is. Alkalis, on the other hand, contain hydroxide ions, or OH-. And yeah, the more of those you have, the more alkaline the solution becomes. And we measure all this on the pH scale, which usually runs from 0 all the way to 14. Right smack in the middle at pH 7, we find neutral things like pure water. Anything below 7 is acidic, and the lower that number gets, the stronger the acid is. And anything above 7 is alkaline, and you guessed it, the higher the number, the stronger the alkali.
Okay, let's tackle our final section. Now, this is a really key distinction, and it's something that you higher tier students absolutely need to understand: the difference between strong and weak acids.
It really all boils down to one key idea: ionization. When you put a strong acid, like hydrochloric acid, in water, basically every single acid molecule splits apart, or ionizes, releasing all of its H+ ions. Boom, all at once. But with a weak acid, like the ethonic acid you find in vinegar, it's a totally different story. Only a tiny fraction of the molecules actually ionize at any given moment. And what that means is, for the exact same concentration, a strong acid will have way more H+ ions floating around, and so it'll have a much, much lower pH.
And here is a little gem that often pops up in exams: the pH scale is logarithmic. What on earth does that mean? It means that for every single step you go down the pH scale, the acidity actually increases by a factor of 10. So a solution with a pH of 3 has 10 times more H+ ions than a solution with a pH of 4. And a solution with a pH of 2, well, that's 100 times more acidic than the pH 4 one. It's a huge difference. So after all that, what is the big takeaway? The most important thing to remember is that these reactions are not random. Not at all. They follow really clear, predictable patterns. If you know the acid and you know the base, you can predict the salt. It's that simple. Once you learn the rules for naming the salts and the 3 main types of neutralization, you can pretty much tackle any acid-base reaction they throw at you in that exam.
So here's a final little test for you, just to check your understanding. Why not pause for a second and try it out? What salts would you get from nitric acid reacting with magnesium hydroxide? Or what about sulfuric acid and zinc carbonate? Seriously, if you can confidently work out the products for those, then you're in a fantastic position. You've totally got this.